All right, let me start my timer. Perfect. Okay, I'm so excited that you're all here today. Thank you so much all for coming. Today we'll talk about my dissertation named Robust Policy Generalization and Risk Quantifications. So before we dive any further, I'd like to first dissect this title into two main parts. So in the first portion, we're going to be talking about robust policy generalization. So here, what do we actually mean by policy? Let's first take a dive into that. So think of this scenario where there's an ego vehicle, another agent on the road. So ego is just a fancy way of saying autonomous car. And the ego vehicle wants to make a turn in this intersection. And essentially, the policy is the ego vehicle thinking to itself, OK, well, what do I do in this setting? And this is dictated by a number of factors. So one might be, OK, which direction should I turn, which might be dictated by the path that it wants to take. Do I wait for the car to pass, which is dictated by what we think the other agent might do. How fast should I actually proceed in this intersection, which might be determined by how fast we think that the car is, or whether there's an included other vehicle that's blocking the point of view. So typically, in a very simplified process, the way things work is you collect some driving data, you pour them down to a machine learning model, and gives you a policy on how to act in situations like this. Which brings us to our next problem of generalization. So what would have happened if there were other vehicles on the road and not just one? Can we still apply what we previously learned in terms of our policy? And what if the road actually looked like this, or this, or this? So in this case, how can we actually accommodate for all these different conditions? Now, the holy grail will be to collect data on these specific scene types, pour them to our machine learning model, and get some policy. And for all other different driving scenarios, we could collect data specifically on these scenes, pour them down to the same model, and get customized policy for each, right? But the problem here is that this is too hard to scale. And so we need more robust solutions, which brings us to the first word in my title, robust. And here by robust, what we mean essentially is being low in cost and effort, but being high in reliability. And there's really no shortage of news that we see when policies don't generalize well. So one example is Tesla's not performing well in Australia because they had no kangaroos in their data set. Another one is Asimo, the Honda robot, which confused audience when they were trying to wave their hand to ask a question versus taking out their smartphone to take a picture of the robot. And another one is this Amazon employee getting trapped in the warehouse because shelves were moving automatically. OK, it's all fun and games, but what if the stakes were actually higher? Which brings us to the second portion of my dissertation on risk quantification. So here, by risk, what we mean is likelihood and potential severity of undesirable outcomes. And by these undesirable outcomes, we're talking specifically about things like collisions, rule violations, mission failures, and so on. And quantification is essentially assigning numerical values to those risks. And by this, what we mean is identifying these causal events that cause these undesired events in the first place, and assigning probabilistic approximations on how likely they are. Again, there's no shortage of events when we don't quantify risk properly. One example is the infamous Boeing 737 MAX case, where safety measures were inadequate and confusing. Another one is the infamous Sterac 25 case in the 1980s, where patients were overdosed with radiation because safety measures were not implemented in the software system. And a more recent example is Cruise having a pedestrian being dragged under their autonomous car, which essentially caused their downfall afterwards. So today we're going to be answering these following two questions. In the first half, we're going to try to answer if we can generalize policies robustly. And in the second portion, we're going to see if we can quantify risk of these undesired events happening. In this quest, we're going to propose a couple of methods. The first is an experience filter, which allows zero-shot policy transfers. The second is an agentic reasoning framework that allows us to generalize our policy with respect to some agentic reasoning. The third is a risk quantification method, which uses a backward risk analysis scheme. And the fourth is a scenario coverage method, which maps our exposure to these risks. So today, for the sake of time, we'll be skipping the first part, and I'm going to be focusing on the latter three. And so with that, let's get started. So robots that explore the space for us, robots that are actually on Earth doing surveillance and delivery, and other robots that help us in the medical field. All of these have things in common. All these systems need to scale their autonomy stack by adapting to different unseen conditions. But there are several requirements to do so. To name a few, one of them is to generalize beyond their initial training data sets. Another one is to be robust under uncertainty in inputs and tasks. Another one is to be able to handle different types of inputs. And there are challenges to these. To name a few, the environments are mostly dynamic, so it's uncertain. Most often than not, there's a component of spatial reasoning, especially when there are long horizon tasks. And the other thing is us wanting to have minimal to no change when we generalize these methods. There has been existing work on this field. To name a few, there's methods on seeing graph methods that try to map the environments by constructing graphs. And other methods have general purpose LVLMs using language models to generalize their policies. But they have their own shortcomings, and we'll try to answer a few of them in today's presentation. So some of them of which are, today we'll be presenting a method that has explicit focus on spatial reasoning components. Our method will be domain, but most importantly, task agnostic. But most importantly, we're going to be presenting an agentic reasoning framework through interface tools. So with that, we're entering our first contribution now in what we call a unified navigation stack. And our goal here would be to define a task-agnostic robotic stack that has freeform reasoning and planning. And we're going to be using an agentic reasoning framework for that. And the key idea here would be to utilize these interface tools to allow the agent to freely reason and plan. And we're going to be accomplishing this by accompanying it with a multimodal memory. The work in this chapter belongs to the paper that's in the banner. And thank you, Bernard, for his huge contributions on this chapter. So let's get started. The first step is essentially when we have a task at hand, we want to first be able to generate plans at high-level steps. So think of this example. There's a household with a human and a robot. And the human says, hey, robot, did I put my laptop's lid down? I think it was in the office. And the robot says, OK, I can take a stab at this. To do so, the steps that I would follow would look like this, where I will first try to explore the environment, look at some office, and then I'll enter this office. I'll search for a laptop, and I'm going to determine to see if the state of the laptop is open or down. Next, given a step, which is, let's say, the first initial step, we're going to be determining which action type we'd like to take. So in this context, we've categorized action types into three. The first is if the agent is confident, it can terminate the environment, and if it's confident to answer the question. The second type of actions are actually navigation actions. So as we are traversing this environment, we're going to be mapping it out as well. So one action type might be to pick a coordinate as we traverse this environment. The second one might be, as we'll see, we're going to be mapping out important landmarks to us. So it might be to pick a landmark to navigate to. And third action type is what we call frontiers, which we'll define in a bit, is essentially points in space where we know we can explore but have not yet. But a more important action type are these logical actions, which I want to dive deeper into. So here we have two types of logical actions. The first is what we call information retrieval. So it might be getting information about some backpack in the domain, in the environment. And this information might include things like its position, camera images when we first detected it, when it was detected in time, and so on. So what we've done essentially is we've allowed an agent to access information like this and more through functional calls, which we'll call them in total interface tools, which are essentially these functional calls that the agent has access to at will anytime. Which brings us to the second portion of logical actions, which are abstract reasoning. So say we wish to evaluate if a certain chair is across a certain sofa. Then what we do is, using the information of the chair and sofa that we retrieved earlier, we'd again use these interface tools, which are different functional calls, which will consume this information about other objects, and will append some question to it, such as, are they actually across each other? Then we get a response. And we can repeat this to then pick a navigation action type. We'll see a demo on how this actually works. The third step is, as we take these navigation actions, we're going to be receiving some observations in this space. So here, our observation sensor suite is essentially twofold. We have a depth camera that allows us to see how far we are from certain objects, and we have an RGB camera. And as we receive these observations, we're going to be updating a scene graph. So here I'm going to talk about what the scene graph actually looks like. So these are an observation scheme that we've observed. But similar to this, as we're traversing this household domain, we're going to be receiving some other types of observations in other places. So in total, we're going to be calling these a scene graph. It'll become obvious why we call this a graph in a bit. So as we traverse the environment, we're going to be collecting sensor data, forming a sensor graph. Simultaneously, we'll be mapping out the environment, which allows us to see which parts of the grid are actually occupied versus not. And as we're traversing the environment, we can actually also segment objects that we detect. So objects of interest to us might be a couch, a door, a TV, a stove, an oven, and all that. At the same time, we're going to be able to see which parts that we can traverse in the domain and which parts we can't. The red nodes are important. Those are the ones that we call frontiers. And what they mean are essentially think of like a corridor. We're in the beginning of a corridor. We know we can extend further, but we haven't explored just yet. So we know physically it's spaces that we can go into, but have not yet done so. And at the same time, with the objects that we detect, we can actually group them out to different rooms. So say if I detected a couch or a table, maybe it's a living room, we can cluster objects into what we think they might belong to in terms of their room. All right, so going back, with these observations that we receive, we're going to be updating this scene graph in real time. Then using this scene graph and interface tools, we're going to be updating our memory. So here, let's briefly talk about what memory is in this context. So for the sake of this study, we've identified memory to be as such. We keep track of our occupancy grid map, and we rasterize our frontiers and landmarks on it. And then we keep what we call a textual experience. So looking at this, we have certain frontiers, which I mentioned are geometric spaces that we can explore, and landmarks of interest to us, so think objects or rooms that are of interest to us. And in this context, we can see that the environment consists of a hallway at point 0, which we see on the right, which might extend upwards at point D, and so on. Another example is the hallway can extend to a certain location, and there are objects like fireplace, sofa, and table, and so on. All right, so going back. So scene graph, interface tools, which I've given out in functional form here. So things such as get object location for a specific object, get nearest frontier, get scene graph node, and so on, which consists of our interface tools. Our previous memory, which I had just shown in the previous slide. We can then combine all of these and have a real-time update to our memory. So here you can see now the occupancy grid map is extended because we updated it with our memory. And now we have some more contextual information on what's actually going on in the scene. And this is how we keep track of what we think is happening within the scene. And finally, as we traverse within the environment, we're going to decide if we want to actually continue or to move on to the next step. So in this setting, do we actually want to keep exploring the environment to look at the office, or do we want to actually enter the office now, and so on? So let's see some action. I'm going to pause the video real quick here. So this is us traversing in a household. At the top, we see what our mission is. So in this context, we're looking for a banjo. And the user says, I'm looking for where I put it. It might be in the living room. It might be in the bedroom. It might be in the hallway. It might be leaning against the kitchen cabinet. So on the left figure, what we see is the bird's eye view, the ground truth, which is unknown to the agent. And we're going to see how the agent is moving within this environment. In the middle, we see our camera observations in real time. And on the right side, we see our update in our memory, our occupancy grid map, as well as our frontiers and important landmarks to us. And in the bottom part, we're seeing what we think the agent is thinking at the time. So here, for example, the mission is to explore a living room. Oops, sorry. All right, there we go. So as we're traversing an environment, right now, our first initial objective is to find this living room because it's one of the options that the user provided to us. So we're now traversing in the living room, trying to see if we can find a banjo or not. And the agentic framework tells us that no progress has been made on confirming the banjo's location because it's not here just yet. So we're looking in the living room, it's not here. We're updating our memory in real time. Now that we know that it's not here, we're now trying to find a bedroom, which is one of the options. So we landed in the kitchen. It's not quite what we want, so we're going to turn back away, try to find a living room. And as we go and find our living room, lo and behold, there's our banjo hanging on the wall. We compared our study to different benchmarks, specifically on methods that actually have some pre-math information available to them, and methods that actually interact with the environment like we do. And we noticed that our accuracy is higher than these benchmarks that we compared against, and our lean path length is also significantly shorter. It does come at a cost though. Our overall token usage with a language model is higher. We've also done some ablation studies to see if actually each component of our navigation stack is useful to us. So to name a few, in the top row, we have the no scene graph ablation study, where we remove our scene graph, and we see that accuracy is significantly dropped. In the second row, it's the occupancy grid map itself. Third row is rasterized representation. And lastly, chain of thought. And we see that removing each component individually causes a significant drop in our methodology, thereby hinting that it's the overall cumulative understanding of all of these tools together that helps us with our high accuracy. So to summarize the contributions for this chapter, we have proposed a framework that allows us to create plans and execute them for general purpose tasks. We have these at-will access tools that allows us to have a truly agentic behavior, and thereby allowing us to have a better spatial reasoning, thereby beating our benchmark methods. So I want to revisit the question that we asked earlier. What if the stakes were actually higher? So think of plants that produce nuclear energy for us. Others that do toxic waste disposal. And a domain that's close to my heart, autonomous cars. So all these domains also have something in common. They're all safety critical systems. And with that, there are major concerns about these domains. So to name a few, we want to be able to have real-time safety assessment of these systems. We want to be able to mitigate for future unsafe events that might occur. And we want to move in a direction of certification that's quantifiable. And there are challenges to these as well. So to name a few, the domains are often partially observable and quite uncertain. There are rare and long-tail events, and scalability is often an issue. Along these lines, there has been existing work, specifically on trying to synthesize policies that are safe directly, or trying to validate and verify methods. But they have their own shortcomings. So first of all, they're usually bottlenecked by a variety of events. Another thing is they are unable to explicitly focus on unsafe belief regions, which we will do in our methodology that I'll propose in a bit. And most importantly, with our method that we'll propose now, we're going to have the ability to validate and improve existing policies. And with that, we're going to be entering our second contribution now on backward risk quantification. And I think I'm going to have some water. All right. So the goal here would be to identify these states and beliefs that we know for sure will lead us to an undesired event into the future. And we'll be doing this by charting these unsafe belief regions in the belief space. And this work belongs to the paper you see in the banner. And thank you, SN, for your huge contributions on this. And the key idea here will be to use a Monte Carlo tree search approach, but with a twist. We'll see in a bit. So here I'm going to first talk about what Monte-Carlo tree search actually is. So the way it works is as follows. We start our tree search with an initial belief. So what is belief, you might ask? So think of this scenario where there's a car moving along a road. This car will have its states, states such as its position, velocity, or orientation. But in reality, these states, the actual value of these states, are quite unknown to us because they're hard to observe because of their uncertainty. So with that, we usually keep a belief instead. So in terms of its position, we keep a belief on where the position might actually be located. And we keep probability of where these positions might be. Maybe it's about its velocity, on its direction, or its magnitude, or its orientation, which is its heading angle, and so on. But these states are not just for us. They're also for other cars and other agents on the road. So if there's a truck, let's say, in front of us, we also keep a belief of these states as well. So perhaps about its shape or size. So if we're looking at this van or truck from behind, we might not know how long it is. Maybe about its intention, so we don't really know which direction it's going to take afterwards, and so on. And all of these combined are what we call our belief, which is essentially our understanding of the world. And that's what we see as represented on the right-hand side with the green node. So at each belief, there are certain actions that we can take. Here, the shade of these squares denote the probability of us taking an action. So thinking about what actions are, think of a situation where we are heading towards a pedestrian at a pedestrian crossing. And at a situation like this, we might have two actions that we can take, either to slow down or to speed up. And let's say we choose to speed up, which is the action that we pick. As a result, we might receive some observations, which is usually through a sensor suite like LiDARs, radar, and a camera. And we represent these observations with these circular nodes in the same tree search. And with these new actions and observations, we essentially update our belief, which is our understanding of the world. And we can really repeat this as many times as we want into the future. And at some point, we're going to be reaching these final loads of beliefs, which we think are going to happen t time steps from our initial belief, which are the red nodes here. And so MCTS is great at looking ahead for future events. And notice here, which is going to be important, there's only one initial belief, but multiple final beliefs. So the real question now is, what if you instead wanted to look at causations of the final event instead of actually simulating them forward in time? So let's do it backwards. And so in this section, we're now proposing what we call a backward Monte-Carlo tree search. There is going to be quite some oversimplification of math here, which I'm going to skip for the sake of time. But the main idea is as follows. So instead of an initial root node, we're going to be starting from initial leaf node, which we call the final belief. Then we can sample what actions we could have taken that will have led us to that final belief. Similarly, we sample observations that could have led us to take that specific action. And we can repeat this as many times as we want, backwards in time. And at some point, we're going to be reaching these initial beliefs. So now notice that we have multiple initial beliefs from a single final belief. So OK, great animations, but how is this actually useful? Well, it's useful because if that final belief that we start this tree search from is some unsafe event, so say it's an event of a car accident, a collision, then as we construct the tree upwards, these initial nodes that we find will be events that we'll know will for sure take us to that final event that is unsafe with some probability. So now we've branched out backwards in time to discover these initializing events backwards. And so if you were to actually simulate them in forward, you would have non-zero probability of reaching that undesired final event. So going on to experiments, think of a setting where an ego vehicle is at a four-way intersection crossing. The ego vehicle wants to do a certain maneuver, and it's uncertain what the other agent might do. So before we get into numerical results, I want to show this figure first. Let's dissect what this figure is telling us. So we see two different bar types, red and blue. The blue ones are essentially what probabilities you would have for each time step backwards, which is the x-axis. So here time steps are at 0.1 seconds, so they're at 10 hertz. So one time step backwards is essentially 0.1 seconds before a collision. And the probabilities are essentially the probability of a collision. So here what we find is the backwards Monte Carlo tree search method is a strict lower bound. This is useful because it tells us that at any given instance in time, we are at least this much unsafe. Another result that we have is essentially telling us how many forward search must I have done to have the equivalent of one backward epoch. And that tells us that one backward epoch is essentially equal to almost 100,000 forward simulations, which tells us how scalable our backward search method is. But I want to show some numerical results to see the actual power of the backwards Monte Carlo tree search method. So here there's a large table. I'm going to give it part by part. We're going to be simulating these nodes backwards in time. So in the first layer, we're backwards 0.1 seconds. The tree has 49 nodes. And the statistics you see are essentially statistics on collision probabilities. So we have median, minimum, median, mean, and maximum probabilities of collisions. And we can really do this for as many steps as we want. But here, I want to specifically focus on one specific column, which is the median here. As you can see, as we are going more backwards in time, the probability of crashing decreases. And this makes sense because you have now more time to save the situation before a collision. And this is the initial policy that we first had when we constructed our tree initially. We can do the same after retraining a policy on the belief nodes that we know to be unsafe. And again, looking at the same column over here of median. And look what we have here. By detecting these unsafe regions in the belief space and retraining our policy specifically on these unsafe regions, we've significantly reduced the probability of crash to be occurring, which tells us now by identifying these unsafe regions and training specifically on them, we can actually perform significantly safer. So to summarize the contributions of this chapter, we've constructed a tree search method that's going backwards in time that allows us to identify these beliefs that we know for sure will eventually transition to an unsafe event in the future. There's a method to compute these transition probabilities, which we have skipped for the sake of time, but it's in our paper. There's also a method that we show how you generalize this method to any belief in space. So here we've discretized them, but you can actually generalize these as well, which is also omitted in this presentation, but it is in our paper. So with this method, we've seen where risk lives, but now we actually want to measure how often we visit it. So backward analysis was great because it can flag danger zones. We'll now move into scenario coverage, which will help us map our exposure to them. And so we're entering our third contribution in what we call the agent scenario coverage, which our goal will be to find low-effort methods to automatically categorize the events that we've observed thus far. And we're going to be taking an approach in what we call distilled labeling. And the key idea essentially will be to use pre-computed embeddings that are almost always readily available from the perception stack, which allows us to avoid any redundant computation. And we're going to be distilling human and language model annotations. I'm going to have a water real quick before we move. Let me see what we're doing on time. OK. All right. So there's been some work done on this as well. This time I've split the work in two sections of self-driving cars and domain agnostics. But there are some bottlenecks, again, to existing works. So our improvements I will propose will be as follows. We'll see that once we train our model, it's going to be extremely cheap to scale it. We're going to be leveraging these embeddings that are already available to us, therefore cheap at cost. But most importantly, we're going to be able to handle these complex but sequentially reasoned events. So let's dive into it. This is a scheme that I showed in the previous slides where Typically, an agent takes an action in some environment. As a result, receives some observations which are from the sensor data. And what usually happens afterwards in a navigation stack is that we represent these observations in some latent space or some embedding space. And with those embeddings, we're going to pass them to a navigation stack, which will then go back and, well, pick a new action to us and repeat. And so what you can actually do here is, with these raw observations, like camera data, you can actually ask help from a human. Given some coverage definitions and requirements, this human can tell us what exists in this context versus not. So here, I want to dive deeper into what coverage definitions and requirements are before we go any further. So let's focus on this little box over here first. So here I'm showing a data set that's actually open. It's the SHARP2 data set. It's available from the Virginia Tech and the Federal Highway Administration. It's essentially a guideline that tells us how a car on the road might behave. So let's look at what this table actually is. There are a couple of groups here that are categorized by the interaction of a certain car with another car. So in group number 1, there's only a single driver. There's no other car involved. In other groups, there are other vehicles involved. So group number 2, for example, are interactions of 2 different agents that are in the same traffic way, in same direction, and so on and so forth. And we have multiple groups as such. Within each group, we have different categories. So let's say group number 2, there's the group number D, which is rear end, which tells us there's a category of rear end collisions that occur when 2 cars in the same traffic way and same direction. And counts are essentially how many different ways these collisions can occur. So to give some examples here, group number 1B, for example, where a single driver has a left roadside departure. So one group is essentially traction loss, which is the vehicle losing its traction and thereby departing from the left side. Another example might be for group 2E, where we have a forward impact. One of the categories is to avoid collision with object. And what essentially happens is, green is the ego vehicle here, and to avoid a collision with that circular object, it makes a rough maneuver, and thereby leading it to crash to a different vehicle on road, and so on. So when we talk about coverage, essentially, we're talking about having seen enough of these different types of events, so we know we can perform adequately well in different scenario types. So going back to our figure over here, we can ask a human to label what they have seen. So true or false binary. Is there a collision rear end? Is there a departure from left side road? And so on. But you can already see that this is extremely expensive. So what we can then propose is, OK, instead of having a human do this, let's use a language model, right? So we can consume those same raw sensor observations, like camera, LiDAR, et cetera, observations. And we can fine-tune an LVLM, which consumes what we think the human might do and learns from the same coverage requirements and definitions. Now, although this is cheaper, it's still quite costly. I'm going to be skipping here on how we fine-tune the LVLM for the sake of time. So we want a better method, essentially, which is what we're proposing here, a distilled surrogate model. So this surrogate model will essentially consume what we think a language model might do. But instead of using these raw sensor observations, it's going to be using directly those embeddings that we have as a part of the navigation stack. Well, this is great because now we can throw away all this part. And you can see it's significantly cheaper to infer because embeddings live in a smaller dimension space than these raw sensor observations. At the same time, they're a byproduct of the navigation stack, so you have minimal implementation effort. I'm going to be showing some experiments that we run with respect to this. So although the data set that I've used was proprietary, I'm going to be showing you examples of an open data set. So here we've used video events of dash cam footages that are near collision or collision. I want to first show what a near collision event looks like. So here we're going on the road where a car is trying to cut in between us, causing a near collision event. Other types are collision type events where trigger warning, there's going to be an accident with a cyclist on the road. So it might look like this. As we're traversing, and we're actually passing on a green light so that we have the right of way, but a cyclist enters our path, he survives, don't worry, and thereby causing a collision. So these are the types of data that we've actually trained our distilled model on. So with that, I'm going to move into the results here. So we have accumulated results for these different groups that we're interested in. Group 1 is not here because it doesn't involve any other agent on the road. So we have these group types 2, 3, 4, and 5, which tells us what other types of interactions that might have occurred. And we've computed these macro scores for precision, recall, and F1. So this first portion consists of a data set that has a training amount of 8,000 scenes and test of 2,000 scenes, where we're trying to mimic that human annotated labels through the LVLM fine-tuning. But more importantly, which is the second part, using those language model results, we now distill that model with the embedding space, which tells us that the macro averages that we have are still quite significantly close to the language model results that we have. But more importantly, it's 1/10 of inference time, about 41 times more efficient in memory. So in terms of summarizing our contributions here, we introduced a framework that allows us to efficiently scale and label these data in terms of coverage. And we propose this by proposing a lightweight surrogate model to essentially replicate these conflict labels using only latent sensor representations. So with that, we're ready to conclude our presentation for today. So today we split our work into 2 main sections. Where in the first part, we talked about robust policy generalizations, and we tried to answer, can we generalize policies robustly? In the second portion, we talk about risk quantification, where we try to answer, can we quantify these risks of unwanted events of happening? And to do so, we proposed methods, which we discussed today together. I want to talk about some future directions that I think are possible. So for the first agentic part, the directions that I would recommend are going into adaptive replanning. So we replan adaptively within the environment. And we want to optimize resource efficiency because right now our token usage is quite high. In risk quantification part, extensions to continuous domains would be a good way to go in directions in the future. In the scenario coverage part, identifying these event time frame intervals directly would be of great use. These are the publications that I had throughout my PhD career here. The blue ones are the ones you see that we presented today. And with that, that is the end of my slides. Thank you all for coming in today.